Optical tubes are normally named by their primary lens or mirror diameter, such as 127 reflector or 72mm refractor. However, camera lenses are normally named by their focal length, such as a 200mm zoom. In naked eye astronomy, what you can see is determined by the diameter of the primary lens or mirror in your environment. Head over again to astronomy tools and calculators. Here you can see a telescope with an aperture of 125mm. Will have a limiting magnitude of, I'm going to say, plus 13.18 or plus 13. You'll understand why I'm saying plus in a minute. And a telescope with an aperture of 72mm would see a limiting magnitude of just about 12. Note the tip at the bottom of trying out what you can see with the naked eye, which has an aperture of 7mm. If we look on a table of apparent magnitude, here I am on Wikipedia, you can see that the Sun obviously is visible at -27. A full moon is -12. With a 72mm aperture, we could just about see Phobos, the one of the brighter moons of Mars. And with a 125mm aperture, we would just about be able to see Pluto. Mind you, all these are just little dots of bright light in the sky. That table assumes that you're in the perfect seeing conditions in a Bortle 1 area. If we look at the Bortle scale on Wikipedia, we can see with a 12.5-inch aperture, we should be able to see something with a magnitude of 17.5. If we scroll down to a Bortle 8 area with the same aperture, you'd only be able to see something of a magnitude of 13. However, for astrophotography, the important factor is the F ratio, which is focal length divided by the object lens diameter. It's often written as F over N, i.e. F over 2.8. It is well known in photography world as the f-stop or f number. So in this example, it would be an F ratio of 4. So think of it like a funnel. So the wider the net, the faster the photons are going to be collected. The F ratio of an OTA becomes a measure of how many photons are being focused onto the eyepiece or sensor. Each f-stop in the sequence f1, f1.4, f2, f2.8, etc. is a half of its predecessor, so f4 collects half the light of f2.8 and a quarter of the light of f1.4. The term fast is a throwback to camera film, but now used to describe an OTA of about F ratio 7 or less. I've added that information to our spreadsheet of definitions, which you'll be able to upload by going to the More section on YouTube. Using a by 2 Barlow lens has the effect of slowing down the light gathering capability by a factor of 4. Similarly, a reducer will have the opposite effect. We previously noted how DSOs leave a trail for any exposure over 30 seconds and how a tracking mount can enable longer exposures. So although the F ratio is important for astrophotography, a good tracking mount can mitigate a higher F ratio restriction by enabling longer exposures. We can add to our challenge of choosing the right OTA for your telescope by not only taking into account its field of view, but also its F ratio value.